Once we have described the Hartree approximation in the general context, we're going to apply that for the uniform electron gas, which is the model that we are considering first in order to describe the physical properties of a solid, the simplest model we're considering. Okay, first let's remember which are the Hartree equations that we need to solve. These are the Hartree equations in the general context here, and these are the equations that we need to consider in order to get the wave functions, the electronic wave functions for the electronic states. Okay, for the uniform electron gas, in this case, the ionic contribution to the potential energy like term we have here is given by that expression here, where the ionic or nuclear charge density, this rho ion here, is equal to N over V. So once we have that, now we have to solve this equation. And actually, it's very quite straightforward to see that electronic plane waves, these equations here, where the spin state can be anyone, because actually the equations are independent of spin, so it's a degenerating spin, are solutions of these Hartree equations. And in order to see that, what we are going to do is we are going to analyze this term, the electronic contribution of the potential energy like term. So this is and for that we're going to plug these plane waves here. We're going to plug these plane waves here. So we are doing that, the square of the modulus is 1 over v. So instead of this one, we have 1 over v, which is independent of j. So when you are doing the summation of these j states, what we have to do the summation over all j states, but this I state, we have n minus 1 terms like that. So you have a prefactor of n minus 1, which actually, considering that the number n is huge, so removing 1 is not going to be a big effect here, and the final result is going to be approximately the same as n over v times this integral here. As you can see, this contribution here is actually the same as the ionic contribution, but with a negative sign. So actually, summing these two terms, they are cancelling each other. They are cancelling each other, so that the ionic contribution and this screening effect of the rest of the electrons that appear here are cancelling each other, and then the Hartree equations that we are getting for the uniform electron gas are actually very simple. Basically, we have the free electron-like equations, where we know that plane waves are the solutions of these equations. So therefore, we are proving that within the Hartree approximation, the solution we have for the electronic states are actually plane waves. Therefore, within the Hartree approximation, the solution we are getting is actually the same as within the free electron gas approximation. So there is not there's not anything new we are having here. Therefore, everything like the ground state energy and all the solutions we had for the free electron gas approximation are the same as the ones we are having for the Hartree approximation. Therefore, nothing new. We are not having nothing new for the uniform electron gas within the Hartree approximation. Therefore, we need a step further in order to have something new.